So I thought I'd tell you about some fun stuff that I stumbled into in the last 6 or 7 years when I started working with Professor Subir Sarkar, who's really the leader of all of this, but also with Roya Moai and Jacques Collin, who are at the Institute Astrophysics in Paris, and Sebastian von Osseger, who is now a postdoc at Oxford, and Nathan Seacrest, who is an astronomer at the US Naval Observatory. And this is about the cosmological principle. So, the cosmological principle is a foundational idea, a central dogma in present cosmology, and it is somewhat vague. It is often stated as the universe is isotropic and homogeneous, with caveats like it is statistically isotropic and homogeneous on large scales, etc. And what it basically means is that we believe there are no special directions or special positions in the universe. If there were special directions, then it would look like this. And if there were special positions, it would mean that the place where we are is somehow different from other parts of the universe. And neither of these are acceptable under the cosmological principle. It was stated by Edward Arthur Milne back in 1939 or so, as there are no special positions or that the universe presents the same general aspect at every point. And the Copernican principle is also, it's in some sense, part of it, that we are typical observers. There's nothing special about us. And the advantage of this rather vague idea is that it enables an enormous simplification in the equations. You have the Einstein field equations, which are monstrously complex and hard to solve. But you don't have to worry about all of that. You can just use the Friedman equations for cosmology as long as you believe in the cosmological principle, which, and the Friedman equations, as you know, contain only one dynamical degree of freedom, which is the scale factor, which explains how the universe is expanding. And you get these simplified ideas like the cosmic sum rule, which tells us that the density of matter, of curvature, of radiation, and of the dark energy, all as if you take a ratio with respect to the critical density, then it should all add up to one, etc. So the cosmological principle is what allows us to do these things. The cosmological principle today is a descendant of a more perfect version of the cosmological principle, which also posited that we were in no special place and time, that our position, our the time we are at in the universe is also not special in any way. It is equivalent to any other time. This led to the idea of the steady state model of the universe, which was abandoned in 1964 or around those time. Though I'm told that at our institute, at the Tata Institute of Fundamental Research, there were people who believed in the steady state model till much later on, and it was abandoned around the time Hubble expansion, and the idea that the steady state model should be abandoned started out when the Hubble expansion was discovered, but the discovery of the CMB and the idea that there was a big bang in the beginning. Then led everyone to abandon the more perfect version of the cosmological principle and settle on the one we have today. And so the Friedman equations, which were first written down in 1916, at a period when we didn't even really know that we were part of a galaxy, when we thought the entire universe kind of looked like our galaxy, we continue to use them even today for cosmology. Now, there are other statements of the cosmological principle, again in words, which is that it is sensibly isotropic and homogeneous when averaged on large scales, etc. And if you look at, for example, Weinberg's textbook on gravitation and cosmology, there are some succinct observations he presents about it, which is that the real reason, though, for our adherence here to the cosmological principle is not that it is because it is correct, but rather that it allows us to make use of the extremely limited data provided to cosmology by observational astronomy. If the data will not fit into this framework, we will have to conclude that either the cosmological principle or the principle of equivalence is wrong. Nothing could be more interesting. So what Weinberg is telling us is that at the end of the day, the cosmological principle is a statement about information. If someone told you a finite three-dimensional solid, you just assume a sphere in your mind in the absence of any additional information, because the sphere is the solid that you need the least amount of information to specify. You just need to know the radius or the diameter. You don't need to know more information. So this is what the cosmological principle actually is. It is a priori assumption that we made in order to make use of data, assuming symmetries which we were unable to test in those times, but today we are able to test them. And so, with today's data, however, there is this idea that there's nothing to worry about. So, if you check Wikipedia, for example, it will say that data from the Planck satellite show the universe to be highly isotropic. And we know this from the fact that the monopole temperature of the CMB is about 2.7 Kelvin, and the anisotropy in it is at the level of a few microkelvins, few tens of microkelvins. So this the fact that the anisotropy is 1 part in 10 to the power 5 suggests that the universe is highly isotropic. And so then this the temperature field on S2 can be expressed in terms of the spherical harmonics, and you can sum up the squares of the of the M modes, and you get the power spectrum. And this curve is well described by linear perturbation theory around the Friedmann-Lemaitre-Robertson-Walker metric. And by fitting that to the data, you can extract the parameters I showed you, omega m, omega lambda, etc., and which tells you that the universe is 68% dark energy and 27% dark matter, and so on. So what is said is we observe a statistically isotropic Gaussian random field of small temperature fluctuations, fully quantified by the 2-point correlations, which is the angular power spectrum shown here. Now, those of you who are more familiar with this already know that this picture is quite dressed. For example, in reality, you don't have data where the galaxy should be because you can't see through the galaxy, and you have to do quite a bit of infilling to get this. But more than that, I would invite you to look at this plot and see that the data point for L equals 1, which is the dipole, is not shown here. And the reason is that if it were to be shown, it wouldn't fit in this plot. It would be 4 orders of magnitude too high. That is because there is a dipole in the CMB at the level of a few millikelvin, so 100 times larger than the small angle anisotropies that were shown in the previous slide. So if you have an anisotropy of this at this level within the CMB, you can of course ask why are you saying the universe is the same in all directions? And the typical cosmologists tell you, oh, Rameez, don't worry about it. It's just because we are moving with respect to this frame in which the universe is isotropic. And it is only due to our motion with respect to the rest frame of the universe that we have this large dominant dipole anisotropy. And we can fit the size of this dipole anisotropy to expectations from special relativity, and we extract that the velocity of the heliocentric frame, the frame in which these observatories were, with respect to the rest frame of the universe, is 369 plus or minus 2 kilometer per second in a specific direction. And because this is described by just special relativity, the idea is that it is purely kinematic. It is arising only because we are moving with respect to the rest frame of the universe. So I keep hearing some sounds. Is anyone trying to ask a question, or is there a problem? Am I still audible? So this CMB dipole is what we are going to talk about today. If we are moving with respect to the rest frame of the universe, we expect a concurrent similar dipole in samples of catalogs of objects you see in the sky, especially and if they are flux limited. So you count all objects you see in the sky in a specific and all around the sky, and above a specific flux threshold, you expect the angular distribution to increase in the density of the number of these sources above a flux threshold to be higher in towards the direction of your motion due to two separate effects. One is special relativistic aberration, that is notions of length along the direction of your motion are contracted due to special relativity, which means that angles that you measure are shifted towards the direction of your motion by this expression. And so with a velocity of 369 kilometers per second, which is about 1/100th of that of the velocity of light, you expect 1/1000 the velocity of light, you expect an anisotropy at the level of 1 part in 10 to the power 3. The other effect is that in astronomy, when we measure the flux of an object, we are usually integrating the number of photons within a band. And if you're moving towards an object, we know that astrophysical objects usually are emitting according to power law. And so, if you're moving towards or away from an object, the band in which you are counting the number of photons shifts, and as a result, objects that were too dim to make it to your flux limited catalog in the direction of your motion will now appear brighter, and they will appear above your flux threshold that you're cutting. Basically, the effective band in which you're counting the number of photons shifts, and these two effects together are captured by this expression. So I'll quickly explain to you what X and alpha are. Alpha is basically the spectral index, which captures how much brighter an object will become because you are moving towards it, and X is the index of the flux function, which I shall show you soon. So this expression was first written down by George Ellis and John Baldwin in a seminal paper which they wrote down in 1984. And they also looked at the velocity of the CMB dipole as that was inferred from the CMB dipole as was known then, and concluded that you need order of 1,000,000 sources to detect the CMB dipole velocity in flux limited catalogs. And in their paper, in conclusion, they say if the standards of rest determined by the microwave background radiation and the number counts were to be in serious disagreement, one would have to abandon either the idea that the radio sources are at cosmological distances or the interpretation of the cosmic microwave background radiation as relic radiation from the Big Bang or the standard Friedman, Lemaitre, Robertson, Walker universe models. Thus, comparison of these standards of rest provides a powerful consistency test of our understanding of the universe. So, the basic purpose of this talk is to allow me to impress upon you, audience, that the situation anticipated by Ellis and Baldwin in 1984 now confronts us. This was first hinted at by Ashok Singhal in 2011 when he looked at the National Radio Astronomical Observatory's Very Large Array Sky Survey, which has about 1.7 million sources, about 2.5 millijansky. So this is a radio survey done from a ground-based radio telescope at a frequency of 1.4 gigahertz. So it was at the northern hemisphere site. So it doesn't have sources below a declination of minus 40.4 degrees. And the X you saw in the expression before is basically this index, which describes how many sources are above a flux threshold as a function of the flux threshold. And you're interested in the X at the value of X very close to the threshold. And so this can be quantified from the data itself, as well as the spectral index of the sources, which can be measured. And now such a catalog will, of course, you see that there are features along our galactic plane. So you want to remove all of that. And even though Ashok Singhal claimed that there was an anomalously large dipole in this distribution, the statistics of that remained questionable and people were not really convinced. So we decided to construct a more all-sky catalog by patching that together with the Sydney University Molonglo Sky Survey, which is at a different frequency but had a similar beam width, etc., with the Northern Hemisphere survey, and is in some sense considered a sister survey of NVSS. And we put them together. Now, the thing is that NVSS is considered complete in the sense that the people who did the survey believe that every source in the sky above a flux threshold is contained in the catalog only if you impose much stronger cuts on the flux, so about 10 millijansky or so. And once you do that, in total, you create such a catalog, you get only about 600,000 sources. And people have done measured the redshifts of some of these sources randomly sampled, and they are all at redshift 1 or so. Though we cannot, redshifts of all of them have not been measured. The vast majority which have been measured have been at redshift of 1 or so. So they are high redshift radio galaxies observed from a radio observatory. And we basically applied an estimator for the dipole, and we found that the dipole anisotropy in the number counts is in within 10 degrees of the CMB dipole direction, but the size of the dipole anisotropy is about 3 times larger than expected, which means that we were to interpret it as due to a velocity. From the expression I showed you earlier, it would be a velocity of about 1,300 kilometers per second. Now, of course, you don't necessarily have to interpret. The only point is that the dipole is larger than expected. And because we have only 600,000 sources and there is square root of n or 1 by square root of n random dipole you expect from just statistical effects, the statistical significance of this is actually quite marginal. I'm a particle physicist. I do not find anything below 3 sigma really compelling. So at 2.81 sigma, it's kind of like just big enough to get me to look more into this direction. But others have looked at other radio surveys, including, for example, TGSS, which is done by GMRT, by the National Center for Radio Astrophysics at in Pune, which is by the institute I'm currently at, DIFR. And they find that a much larger dipole is there in this sample at 5.1 sigma. More recently, others have looked at every radio survey, and they have come to the conclusion that for all analyzed surveys, the observed cosmic radio dipole amplitudes exceed the expectation derived from the CMB dipole. And that is summarized in this paper, Seward et al. 2020. Now, these are all done using ground-based radio observatories, and it is possible that there are some systematics due to the atmosphere, etc. If you present this result to typical cosmologists who believe in lambda CDM, they'll tell you, there must be some systematic, and they'll be quite dismissive. So what we decided to do is we decided to do this test in the infrared, if possible. And for that, we looked at data from the Wide Field Infrared Survey Explorer, which is a satellite that did a survey which was unbiased of the sky over 10 months in the bands of 3.4 micrometers to 22 micrometers using a 40 centimeter diameter telescope that's illustrated here. Two of these bands, the photosensors require cryogen to be functioning. So after 10 months, the cryogen ran out and the band stopped functioning. But even after that, the larger bands continue to function. So there is a post-cryogenic phase. There's a post-cryogenic phase with just the two smaller bands included. This survey generated a catalog of more than 746 million objects, most of which are stars. And the advantage of this survey was that it always looked in a direction which is perpendicular to the direction of the sun to keep the background light, etc., highly uniform. So it had a highly unbiased survey strategy, a selection function of different directions in the sky that is as under control as possible. And it had 4 bands for photometry. And we isolated a sample of 1.3 million quasars under the leadership of Nathan, who is an expert on quasars at the US Naval Observatory. And we analyzed that sample for the dipole in the number counts above a specific flux threshold. And we published this paper in 2021. This was the first paper I published after moving to India and starting a faculty position at DIFR. And our conclusion was that while the direction of the dipole in the quasar sky is similar to that of the cosmic microwave background, which is also what we saw in radio, its amplitude is over twice as large as expected, rejecting the canonical, exclusively kinematic interpretation of the CMB dipole with a p-value of 5 times 10 to the power minus 7. So in frequentist terms, it is equivalent to 4.9 sigma one-sided. Our results are in conflict with the cosmological principle, a foundational assumption of the concordance lambda CDM model. So the sample of 1.3 million sources, if you were to look at its distribution of fluxes, it is given by this. And this is the slope of this curve is what was x. And the spectral indices of these sources is given by this distribution. We can cross-match it with the baryon oscillation spectroscopic survey of SDSS over a small batch. And the redshift distribution is here. So the median redshift is greater than 1, even though there is a small number of sources at low redshift. its sky distribution is given by this figure. And if you estimate the dipole in it using the heel pi fit dipole estimator, this is the value we obtain. We can of course do scrambled trials of the data in a process that we frequentist, or since I'm a particle physicist, I like to do my statistics in frequentist ways, can do. And this is the distribution you expect if the null hypothesis that this is in accordance with the purely kinematic interpretation of the CMB dipole is true, then this is the distribution of the expected dipole. And you see that it is an outlier at the level of 4.9 sigma. But the direction of the dipole is within 23 degrees of the CMB dipole and is consistent within 1 sigma of the CMB dipole. Now, this entire data set, how to produce this data set from the Catwise original data release, how to run these estimators, how to run the Monte Carlo to produce these plots. All of it has been made public on Zenodo and in Jupyter notebooks, and it will enable you to easily reproduce these results because we believe in open science. It is important that all of you should be able to test this on your own if required. More recently, in 2022, we independently used even more conservative frequentist test um, to see how well the two samples we spoke about, VSS and Catwise, are compatible with each other and how much they overlap. And we found that the number of overlapping sources is less than 1%. We created a conservative treatment for them. We slightly expanded the cuts on our Catwise sample, and we now have 1.6 million sources. And even using the most conservative frequentist techniques, we find a 5.1 sigma disagreement with the purely kinematic interpretation of the CMP dipole. And the code and data for this is also public on this Zenodo, and we published this in a paper called A Challenge to the Standard Cosmological Model in Astrophysical Journal Letters here. So some cosmologists do not believe frequentist results because, the universe is not a system that's amenable to repeatable experimentation. So cosmologists are intrinsically philosophically Bayesian, and but that's not a problem. Other authors have downloaded our data and they've run Bayesian estimators on them, and they come to the exact same conclusions. However, the amplitude of the dipole is found to be 2.7 times larger. And in Bayesian terms, just the Catwise sample is at 5.7 sigma tension with the CMB dipole. With the these results support the original findings of an anomalously large quasar dipole, independent of the statistical methodology used. So this result has had quite a bit of attention in the popular media. Sabine Ossenfelder has made this video, which now has more than 1 million views on YouTube. New Scientist has done two articles. Quantum Magazine did an article. The Wire Science, which is Indian, did an interview with me, and there's this article. But more important than the popular attention, the scientific community itself has been motivated by this to rethink various aspects of foundational aspects of cosmology. So we have a small community around us that's slowly growing. The particle data group in 2022 highlighted this as one of the principal anomalies in cosmology. Reviews by 4 Nobel laureates, so Adam Rees, Saul Perlmutter, George Smoot, and also now Jim Peebles. So reviews containing these 4 people in their author list have highlighted this right beside the Hubble tension as an emerging significant anomaly in cosmology. So this is very nice. And just to summarize what this anomaly is, so because the x and alpha values for each sample and depending upon which wavelength and band and stuff you use is different, the size of the pure dipole in each sample within the purely kinematic interpretation of the CMB dipole is different. So you divide that out. So the ratio with respect to the purely kinematic interpretation is what is plotted along the x-axis here. And one would be the case where it is purely kinematic, but all samples, as you can show significantly larger values. The uncertainties shown here are 3 sigma. Our result is here. Recently, there are more. There are other samples that claim much larger anomalies. There are now almost 300 citations, or actually close to 400 citations of these two papers we have pointed out. Um, if you include the radio results, also now more than 500 citations of our results, and we ourselves are just a small part of the community. There is a larger community of Thilo Sievert and Wagenweld and a bunch of people around the world who are doing this with all sorts of catalogs. There are around 10 odd papers that also look at other data sets and claim consistency with the kinematic interpretation. We are in the process of writing up a reviews of modern physics colloquium explaining why that is and how that doesn't really change our mind. But if you look at it, what you'll see is basically you'll see results like this Mal's distribution. So you'll see that it is compatible with the CMB dipole, but it is also compatible with our result, which is this orange one. And that's because, so basically, if you take two small catalogs, the uncertainties are so large that it'll be compatible with everything. So you can take such data sets and write papers claiming that the observed matter dipole is consistent with the CMB dipole. But what you really need is a large sample of more than 1 million sources like we assembled to be able to say conclusively what's going on. And because of these results, a lot of upcoming surveys, especially the Square Kilometer Array in its red book, as well as Euclid, Spherex, etc., have put these as a key science goal, testing foundational assumptions of cosmology and whether the CMB dipole is purely kinematic. So now I would like to get a little closer and look at what is causing this the motion of 369 kilometers per second in the direction of the CMB dipole. An object like Kobe or Kobe Firas, which measured the CMB, is in motion around the Earth, but that's just a velocity of about 7 kilometers per second in lower Earth orbit. The Earth itself is in motion around the Sun, but that's just a velocity of about 369 kilometers per second. And both these motions, they get averaged out significantly over human timescales. We go around the Sun, 80 to 100, or maybe, I don't know, depends on how old you plan to live, but of the order of 100 times around the Sun during our lifetimes. Now, the Sun goes around the galaxy with a velocity of 220 kilometer per second or so, which has been measured now in using parallax and so on. And this velocity is not something that really, the direction or the amplitude doesn't really change over human timescales. In fact, the Sun takes about 260 million years to go around the galaxy. This means that in the entire 300,000 year history of anatomically modern human beings, this vector, its direction has changed by less than a degree. And then the galaxy is moving with respect to the local group with a velocity of about 40 kilometer per second or so. And it turns out the velocity with respect to which the Sun is moving with respect to the CMB, as inferred from the CMB dipole, and the velocity with respect to and the velocity with which the Sun is moving with respect to the galaxy, as inferred from parallax measurements, are counter aligned to within 7 degrees or so, which means that the local group of galaxies is moving with a velocity of about 600 kilometers per second with respect to this cosmic rest frame, the rest frame of the universe. And these are all widely accepted facts in astronomy today. This plot I'm showing you is a plot from George Smoot's Nobel lecture in 2006, which he gave. So no one questions these to be facts. They are accepted to be the case. The question then, the interesting thing is, how far, so where is this cosmic rest frame? So you can ask not just the local group. If we go a little further out and start looking at matter in larger and larger shells around us, it turns out that the origin of this motion within those shells, the fraction of the velocity, as we go out in larger and larger shells, we don't find that all the velocity is originating with that shell. We find that the shell itself is also moving in that direction a little bit. So this is a nice summary from a paper that was published by Brent Tully and my collaborator Roya Moyai in 2010. As you can see, even out to 150 H inverse megaparsecs, you have not really converged, and the entire bulk volume of 150 H inverse megaparsecs around us appears to be still moving in the direction of the CMB dipole. Uh, of course, the uncertainties are quite large here, and you can say it could be compatible with zero. You can see this illustrated better in this plot. So these data points you see correspond to the velocities of of a sphere around us of this radius, um, and the average velocity of that sphere. That is what is plotted in these data points. The bands correspond to the velocity you expect if you were to randomly pick halos from a lambda CDM in body simulation and calculate the average velocity of a sphere around it. And of course, that depends on which it's a statistical distribution. So the width of that distribution is quantified by this band. So if you measure this, I mean, you can see from these measurements that uh, the entire sphere out to 200 S inverse megaparsecs, which is roughly 1 billion light years around us, is still moving with respect to the CMB rest frame, and that too in a direction roughly like the CMB dipole direction. But of course, if you consider the uncertainty from the lambda CDM model, you could always argue that it is compatible with the lambda CDM model. So there's nothing particularly surprising here if you're a lambda CDM diehard. But the idea is that we think of the CMB dipole as originating due to our motion with respect to the cosmic rest frame. But these results, the bulk flow results in the local universe, suggest that it is not just us, but something like the entire universe around us, out to 1 billion light years around us, is still moving with respect to the cosmic rest frame in the same direction, roughly. And this evidence has now gotten stronger. And to see if you have to kind of build sophisticated estimators to see how compatible with this is with the standard model. And in the Cosmic Flows 4 data set, which is compiled by R. Brent Tully, and Tully's group is, they're very competent in understanding their astronomical error bars. I admire them deeply for that. And one of these papers, I think this is from 2023, they point out that this has just 0.003% probability of occurring within a lambda CDM universe, the large bulk flow they observe, and that this is now in increasing tension with the standard model, so at more than 4 sigma. Now, this forces us to consider a theoretical scenario which is being presented by Christos Sagas, who's a mathematical relativist at the Aristotle University in Thessaloniki. And Christos basically explains it using a figure like this. He considers a background cosmology, then he considers a region within that universe where matter is moving. And then he uses covariant and eigenvariant linear relativistic cosmological perturbation theory to calculate what observers who are sitting inside the bulk flow should measure for the rate at which the universe is accelerating. So Q here is, I'll show you later what Q is. It's called the deceleration parameter. And his basic argument, which he also presents independently using the peculiar Ray-Chowdhury equation, in a sequence of papers, there are more than 6 or 7 papers. They are quite interesting. Is that if you're sitting in the middle of a bulk flow and you also have a motion with respect to the motion around you, then you can start measuring a very different expansion rate or acceleration to the expansion rate of the universe than you would expect from the Friedman equations which describe the background cosmology. And he explains it in words in its abstract like this. This implies that observers experiencing locally accelerated expansion as a result of their own drift motion may also find that the acceleration is maximized in one direction and minimized in the opposite. We argue that typically such a dipole anisotropy should be relatively small and the axis relatively fairly close to the one seen in the spectrum of the cosmic microwave background. So we decided to test this hypothesis using a catalog of. So basically, Christos uses these arguments to also contest the idea of lambda. Like various physicists, including my mentor, Professor Subir Sarkar, he does not like lambda. You theorists have various reasons for not liking lambda. I'm not going to get into that yet. But Christos' idea is that it could just be that the kinematics of the bulk flow has been mistaken for the idea that the background cosmology itself is accelerating. And so he points out that the effects of the bulk flow could be the reason we infer accelerated expansion from the kinematics of the local universe. And we decided to test that with a catalog of 740 uh, type 1a supernovae, a compilation of their observations. So this paper was published in 2019, but we actually submitted it to a journal in early 2018, and it took more than a year and a half to get published. It was a kind of bizarre experience. It was just my third paper in cosmology. I trained primarily as a particle physicist, um, but it you know the referee response was quite religious and close-minded, and it was a bit like arguments I had as a child with like religious teachers that my parents assigned to me. But to not get carried away, let's just understand what this analysis was about, and to understand that we need to understand what type 1a supernovae are. Type 1a supernovae are thermonuclear supernovae. That is, we believe they are like a white dwarf that is below something like the Chandrasekhar limiting mass, and they are accreting mass from a nearby companion. And the moment this progenitor's mass crosses this limiting mass or the Chandrasekhar limit, then it explodes. So it is believed that uh, because they all explode at a specific threshold mass, which is set from fundamental physics, they should be standard candles. But what happens if you look at data from type 1a supernova explosions, for example, all from within one host galaxy, so they should all be roughly at the same distance, is that in reality they're not actually standard candles. There is quite a large spread of almost one order of magnitude in their peak brightness. What has been observed empirically is that the ones which are falling off faster are actually brighter, and the ones which are falling off slower are actually dimmer. So notice that the numbers along the x-axis are negative, and along the y-axis are negative, and that's because in astronomy, the brighter an object is, the more negative its magnitude is. Objects which are brighter fall off slower, and objects which are dimmer fall off faster. And so, if you add two linear corrections to the data, to the peak brightness of the object, then you see that the scatter is significantly reduced. It's still not zero, but it is reduced. So, this standardization of the light curves is now done according to something called the spectral adaptive light curve template 2. And you have a measure of how fast the light curve is falling off, which is called the stretch, and which band you measured the peak brightness in, which is called the color. And you have these two linear corrections which you need to apply to the measured B band magnitude, and then you can construct a distance modulus using this expression. This is believed to be the quantity that is fundamentally unchanging, because the supernovae are in some sense standardizable quantities. And now you can compare it against the luminosity distance in your fiducial cosmological model to infer the kinematics of the acceleration. So if you were to look at Perlmutter et al. 1999, the Nobel Prize winning paper, in which 50 supernovae were analyzed, this is the quantity that I just showed you earlier, the distance modulus plotted as a function of redshift, and this is the distance modulus prediction from theory. And the evidence for dark energy was quoted as high redshift supernovae, which are these supernovae, were found to be 0.15 magnitude or 15% in flux, fainter than the low redshift supernovae. So basically, the idea that these data points cluster along this curve and not this curve is the evidence for dark energy. The idea that the universe itself is accelerating, and this was done with just 50 supernovae. The paper we wrote was with 740 supernovae. So the SDSS2 SNLS3 light curve analysis, which joint light curve analysis catalog, which in 2014 released similar data for 740 supernovae, can be analyzed using these techniques. So the smooth curve I showed you in the previous plot, you can obtain it from the Friedman equations by analytically integrating them to get this luminosity distance expression. Or you can also use a purely kinematic description. So You can, you can write the luminosity distance in terms of the Hubble parameter, the deceleration parameter, which here is defined with negative sign in it because it was written down at a time in history when people thought the real universe was decelerating. So they wanted the deceleration parameter to be positive. So they defined it with this negative. And they want, yeah. But now we believe it to be accelerating. So the deceleration parameter today is believed to be negative. And then there is jerk, snap, and so on. And you can write a Taylor series expansion for the luminosity distance, as pointed out by Matt Visser in 2004. And what we did is that, in accordance with what Christos Sagas predicts, we take the Q0, the deceleration parameter at redshift 0, and we promote it into a monopole component and a scale dependent dipole component. And the scale dependent dipole component has an exponentially falling scale to it. And once we did that and we used the maximum likelihood estimator to fit the data, we found that there is indeed a dipole in the deceleration parameter, which dominates over the monopole out to a redshift of even 0.1. The value of S we found was 0.026, but Q dipole is about -8. If the lambda CDM model is true, the Q dipole should be 0 and the Q monopole should be -0.55 because it's given by omega m by 2 minus omega lambda. As an a posteriori test, we varied the direction of this dipole. So, because Professor Sagas's papers predict that this dipole should be in the direction of the CMB dipole, and because we at 740 supernovae, we don't really have enough data to really study this properly. For our first analysis, we just fixed the direction to the CMB dipole, and as an a posteriori test, we varied the direction, and we found that actually this effect is maximized just 23 degrees away from the CMB dipole. And so the dipole is statistically significant by Wills' theorem at about 3.9 sigma, while the monopole is compatible with 0. So the idea that there is a monopolar acceleration, which would be what we need, to ascribe the acceleration of the universe to dark energy or a cosmological constant, that is defendable at only about 1.4 sigma. So there is no evidence for an isotropic acceleration. All evidence for acceleration seems to be anisotropic. Now, so the statistical significance of the universe accelerating isotropically is less than 1.4 sigma, or cosmic acceleration and basically dark energy may simply be an artifact of our being located inside a bulk flow, in accordance with the predictions of Sagas. So, the moment we got this paper published, even after 1.5 years of peer review, there were like multiple papers within so Rubin and Hageloff 2019, this paper came out within like a month of our paper and was published within 3 months. They basically came out saying we are wrong, and not in a very subtle way. They just say that we are wrong. And we have had many back and forth with them. We have carefully reanalyzed everything. They also analyze our data very carefully. They're able to reproduce our results. So it's not about being able to reproduce our results, because in this case also we made all our code and now we are making doing the fits, etc. public. The issue actually comes down to two simple issues. The first is that this X and C, the color and stretch parameters, as distributed with the data, and in the analysis that the authors who distributed the data did, were treated as independent of redshift and also independent of sample. The 740 supernovae itself are made up of subsamples, like which are seen according to these color codes, and we treat them just like the authors who released the data did, which is that these X and C distributions have no sample dependence. But these authors, for example, point out that if you plot them, there is a best fit sample dependence. So you should add about 12 additional parameters to enable a sample and redshift dependence to the distribution of these parameters. And once you do that, the evidence for acceleration, isotropic acceleration, actually increases, etc. And in fact, we don't find this to be credible, and you can see that from the following. For supernovae to be standardizable candles, the derivative of this capital M with respect to redshift has to be 0. So if you take the derivative of this entire expression, then for the dm by dz to be 0, you need the dm by dx1 by dz and dc by dz to kind of conspire to cancel out, or as well as dmb by dz, the three of them together to conspire to cancel out. Now, if you enable dp to be non-zero, there is no way then dm by dz is non-zero, and so just allowing these to be redshift dependent implicitly means that type 1a supernovae are not standardizable candles, and then that means that you cannot use them to measure the acceleration of the expansion rate of the universe. A Korean astronomer, Young Wook Lee, has independently made these similar arguments. He also looks at the age and metallicity dependence of this quantity, and demonstrates that actually they are not standardizable candles, that this does evolve with redshift. And he also claims that then there is no evidence for dark energy from type 1a supernova data. This is a Nobel Prize winning discovery, and we don't believe it to be true for the reasons. But this is, this is not the most important issue here. I'll come back to the issue of anisotropy.
Hey,
And
Rameez, could you wrap up in 10 minutes?
yes, sorry. Yeah, I'm very sorry for going over time.
No.
But the basic idea is that we use the heliocentric redshifts because Professor Sagas's predictions explicitly depend on specifying which observer is doing the measurement. The acceleration rate depends on the observer, and our observer is sitting in the heliocentric frame. But the data as shipped with the Type 1a supernova compilations actually provide something called the CMB frame redshift. And the transformation between these two is what the results I showed you earlier are questioning. That is that whether it is actually due to just 369 kilometer per second motion or so. And the bulk flows I spoke about are what goes into this. This expression is something you get from this paper by Tamara Davis in 2011, but it's also something you get from George Ellis' paper in 1987, The Fitting Problem in Cosmology. So I looked into how they had corrected the data, and I don't agree with it at all. In fact, broadly speaking, we have a review as presented here, which you can all read to understand both sides of this debate that ensued. And the basic idea is that these peculiar velocity corrections by which the redshift is being changed, you measure the redshift in the heliocentric frame and then you infer what it should be in the CMB frame by introducing a bunch of corrections. These corrections are not scientific. There are arbitrary discontinuities within them which turn the whole thing absurd. And then the whole thing is also circular logic because the peculiar velocities are explicitly understood to be differences once you subtract out the data. If we analyze it, we see a similar effect. That is, at the low redshift, depending upon which frame you are doing your analysis in, heliocentric frame, CMB frame, or the local group frame, you see a strong anisotropy, a dipole in the deceleration parameter. And this is a paper that will come out in the next week or two, which is led by my student. And this also now allows you to understand the discovery of dark energy. If you look at the 99 paper, you use Vizier or something to plot the directions of all of these supernovae. You see that they were all in the direction of the CMB dipole, and the majority of them were in the direction of the CMB dipole and the bulk flow. The basic idea is that this relative dimming of about 0.15 magnitude between the high redshift supernovae and the low redshift supernovae is being put into the data through these peculiar velocity corrections. And you can see more details in this review that we wrote in 2020. So you may have heard that there is now the Hubble tension, which is the claim that the Hubble parameter has been measured with the uncertainty of 1 kilometer per second per megaparsec, which is the extend along the y-axis of this gray shaded line. And this has led to a crisis in cosmology. And we actually see an anisotropy in the Hubble parameter that is even larger. So you can interpret the ongoing crisis in cosmology in terms of this paper, the analogy that George Ellis provides in this paper in 1987. which is that fitting a Friedlander-Lamaitre-Robertson-Walker model to the universe is just like fitting a sphere to the Earth. The Earth is a sphere. If you were to consider a radius of about 50 kilometers, on an uncertainty on the radius of about 50 kilometers, but if the precision is down to 5 kilometers, then it's not a sphere because the Himalayas are larger. It's an oblate spheroid. The equatorial and polar radii differ by more than 5 kilometers, etc. Similarly, in the previous era, when the Hubble parameter was known only to an uncertainty of about 7 kilometer per second wave parsec, also the universe was well described by an FLRW model. But now that we have it down to a precision of 1 kilometer per second per megaparsec, it is no longer well described by a Friedman-Lemaitre-Robertson-Walker model. It is tilted. The bulk flow in the local universe, what it tells us in some sense, is that the CMB rest frame is not a real idea. I think of it as the idea of the rest frame. The idea of the center of the universe in pre-Copernican times. I think of it as just a mathematical notion that does not have an equivalent idea in reality. So we have now a project in the Dark Energy Science Collaboration of LSST, where we will be testing these ideas using completely blinded analysis for the first time in cosmology. So it's possible that in the previous statements I made, I may have jumped to conclusions, but my student Animesh will do a very principled blinded analysis and decide for himself whether the universe is isotropic or anisotropic. But the basic idea is that with just the first year of LSST data, where we expect to see about 5,000 supernovae, we should be able to see if the if the acceleration is isotropic or anisotropic at more than 6 sigma. So, in conclusion, I believe that the standard model of cosmology, its foundational assumption, the cosmological principle, stands falsified, and the idea of the cosmic rest frame is a cultural myth that we should abandon. We have the cosmic dipole anomaly, which has been established in 4 independent radio galaxy catalogs and also now more than 4, the 5 or 6 independent radio catalogs, as well as one catalog in infrared by us. And type 1a supernova are better fitted by a tilted Friedman model. This is a strong hint towards inhomogeneous cosmological models and the idea that dark energy is not real. So anyone who has access to LSST, you are welcome to join our project because we are open to input from all sides. We don't want to be biased. We want to do a blinded analysis. If you're looking for an interesting review to read, Subir Sarkar was invited by Sheldon Glashow to write about this in the Inference Journal of Science, International Review of Science. So I will conclude here. I'm very sorry I went over time. I was not planning on that, but perhaps.
Yeah. Thanks for the fantastic talk. So, questions?
Yeah, I can hear you.
Okay, I was just wondering. So, if you remove dark energy, I thought that the CMB, the position of the first peak, tells you that omega total is 1. If that is correct, then what do we substitute it with in order to get 1?
So, this omega m plus omega k plus omega r plus omega lambda equals 1, that expression is true only if the Friedman equations are true or if the cosmological principle is correct. Otherwise, there's no reason for them to add up to 1. Now, the basic idea is that because the universe is expanding at different rates at different points and the Einstein's equations are nonlinear and so on, the relativists have long been saying that you should add an additional term to it called omega back reaction, which they have tried to compute, but it's mathematically very complex to compute what that term should be, and it's currently not known. But the basic idea is that there's some rule with which you're doing this kind of accounting is no longer a valid expression for the real universe if the cosmological principle is not correct. So our observation strongly suggests that the Friedman equations cannot describe the real universe, that the Friedman, Lemaitre, Robertson, Walker models cannot describe the real universe. You need something more. Either you need like perturbations around the Bianchi background or something like the Zekeres models that inhomogeneous cosmologists have been talking about. But the basic idea is this, that omega lambda, you infer that way from the sum rule, is a mistake because the sum rule does not apply to the real universe.
Okay, thank you.
Yeah.
Hi. Thank you for a very nice talk. So, my question is about if we have these tensions and discrepant results in cosmology, how would that affect, let's say, Planck results on the total sum of the light relativistic degrees of freedom? Can you comment on that?
The total sum of the relativistic degrees of freedom or non-relativistic degrees of freedom, you mean? So dark matter.
No, the n effect, the number of neutrinos, let's say, n effective coming from Planck result.
Okay. The number of neutrinos.
No, the sum, sorry, the sum of the number of neutrinos, yeah. The sum of the masses of the neutrinos, yeah. Sorry.
The basic idea would be that Planck data needs to be completely reanalyzed because, you know, so there are Planck data has always had these anomalies at the low angles with the quadrupole and the octupole being aligned and there being a hemispherical power anisotropy, etc. And these uncertainties that you see blowing up there in the data, they're not empirical uncertainties. They are actually like cosmic variance that has been added up on top of that. And the basic idea would be that you would need to reanalyze Planck data completely. Now, I am a particle physicist. I worked with neutrino astronomy data in IceCube, and I know how neutrino physics works. And I can tell you various reasons why I just don't buy that the cosmology fits on number of neutrinos, mass of neutrinos, etc. have any meaning. I don't think those are meaningful at all.
Okay, so those just sorry for so those inputs from Planck are taken at very seriously as far as let's say Srivan Vishnu searches are concerned. So I mean, he's saying we shouldn't take them that seriously.
From a point of view of are you going to do a search for sterile neutrinos and decide then, oh, I'm not going to do the search because the CMB tells me otherwise? No. In that case, you should not take it seriously. You should still look for that sterile neutrino if there is particle physics motivation for it.
Okay, thank you very much.
Yes. In fact, I mean, this is just an opinion, but I've looked at this and I've kind of come to the conclusion that there are no problems for particle physics that are motivated from cosmology in some sense. So, we talk of dark matter and dark energy. I don't like. Of course, there are interesting reasons why you can always cast any search for a new particle as a search for dark matter, right? Because you're just looking for anything that's massive and that's new out there, which might not be there in the standard model. So from that point of view, it's nice. It's a nice terminology and it's great marketing. There are also like all sorts of science fiction novels and shows and stuff about dark matter. But I don't buy that there's any actual evidence for any of this in cosmology because I've looked at how they fit the data to the model and how theoretically valid the model is. And I think we are standing at a moment where, due to various anomalies, the Hubble tension and now also the cosmic dipole anomaly, which slowly we are the ones who have started it, that this model will fall apart the same way the steady state model fell apart 50 years ago. So at least that's just my opinion.
Thank you. Yeah.
Any other question? So just let me see if I've got this right. Your results, is the only explanation that you have to give up homogeneity and isotropy, or is there some other component you can add to fix, so to speak, your data?
Well, if you look at the 300 or 400 odd papers that cite our results, the vast majority of them are attempts to save lambda CDM by adding additional components to this. So I can show you I have some backup slides in which I'm considering this. Let me look at this. Yeah. So one important thing is something called the clustering dipole, which is that if your sample is not a high redshift enough sample, then you have, because locally you have you have the Virgo cluster, and if all your samples are low redshift, of course the Virgo cluster will mean that there is more sources in one direction. That could be the dipole. But for example, our catwise sample is very high redshift, and more importantly, this can be computed from linear perturbation theory. We have done that for our sample and is 1/60th of the excess dipole we observe. So that cannot explain it for our sample. But people are coming up with different attempts to kind of enhance the signal somehow for different catalogs and try and explain it. The other attempt I've seen is that there is something called super horizon isocurvature perturbation, which is that after inflation, there is an anisotropic mode left over, which means that the entire Hubble horizon is moving in one direction. So the bulk flow and the tilt, etc., would be naturally explained in that. But this again, if for me, is just an attempt to save the FLRW metric, because inflation is needed as an explanation for how the universe turned out to be isotropic and homogeneous, or to justify justify using the Friedman equations. And now, if you're going to say inflation left behind an anisotropic mode, which then made the universe anisotropic in the beginning itself, and that is why it is anisotropic today. I don't know. I mean, these explanations do not appeal to me. It's I think they're just like attempts to save something that should die.
Well, that's a very clear opinion. Thank you.
Another question were actually 2 points. One is that on said and done, whatever one observes in cosmology, there are small deviations from the main bulk, which is supposed to be homogeneous and isotropic, right? If you give up that, which is fine, I don't have any axe to grind there. What is the replacement? Has anybody attempted something to produce results which are comparable? Or secondly, I mean, if you saw the more corrections are going to go, so for do the new model as corrections to homogeneous and isotropic model, higher order corrections, then the perturbation there itself is questionable.
Yes. So I do.
If you want to replace it, I mean, is there any attempt that alternative model, which is not homogeneous and isotropic, then in mathematical models, I'm not talking about that. From that, any observation and inference has been deduced which can be confronted?
So there are. I was recently at a Royal Society meeting where a bunch of people who were working on things like this were invited, and so there is a guy called Istvan Shapuri. He's I think he's in Hawaii. He has something called the Avera cosmology, which is it's a computational model. It's like an n-body simulation, but it allows the metric to expand everywhere at a different rate, and then there's a coarse graining scale and so on. And they find that, for example, things like the integrated Sachs-Wolf effect, which has long been an anomaly with respect to standard cosmology when the few times it has been measured. It is now better explained by these models, and the model also makes a prediction that the size of this effect or the direction of this anomaly should shift between, or the sign of that anomaly should change between low redshift and high redshift, and that prediction has been confirmed with data and so on. So, broadly speaking, it is things called inhomogeneous cosmological models, which George Ellis and people have been saying for a long time, and is a basic idea. I mean, I don't know, it kind of that is my answer. If I got your question correctly, your voice was not 100% clear, so I may not have gotten your question correctly, but I agree with you that perturbation is questionable. You don't really think cosmological perturbation theory is valid for the things cosmologists are using them for. And there are people who have studied the validity of that and so on, who comment that parameters like omega m and omega lambda are not well-defined parameters, etc. So, yeah, I'm sorry. Is that...
No, I think that's fine. No, heard my question. Okay. Thank you.
Hi Rameez, thanks for the nice talk. I'm curious about one thing which I think you guys have responded on archive, but I'm still curious. So one of the arguments against this supernova thing is that you did not take into account wavelength dependent dust corrections for supernova 1 is.
So that it basically...
There, but can you just repeat it? I'm just
Yeah, so it is basically this. They, in the analysis which involves Sol Peruter and Adam Rees, they treated the color and stretch corrections as sample and redshift independent. We treated it exactly the same way. Then Rubin and Hayden and Rubin and Haitloff came along and said, no, that is wrong. If you look at this distribution, it is like this. And if you treat it that way, then you see more evidence for both isotropic acceleration, but for isotropic acceleration, but it like I said, if you decide to do this, the argument that supernovae are standard candles themselves fall apart. I don't so. I mean, this is being acknowledged by various authors who cite both sides now, that it is just a convenient argument.
Okay, anyways, yeah. Okay.
The other thing is there is a mass step correction which we did not take into account, which they do, but we find that it has no implications at all for the amount of acceleration we infer. So there is also a difference of opinion on the statistical method to use, but there again the community is converging in the direction of us, in the sense that supernova cosmologists themselves are starting to use maximum likelihood estimators, which Subir and a student introduced first to the community. They were using something called the adjusted chi-square, where they adjust the intrinsic scatter term by hand until they get a perfect fit and so on, which is again has issues of circular logic in it. And yeah, so this is, when somebody comes and tells you a Nobel Prize winning result is wrong, maybe don't believe it. Take my views also with a grain of salt, but you can read this review that we have written in EPJST, and you can decide for yourself. This review, Mohayai et al. In 2021 is quite detailed, and it covers every perspective, and we also point out where our own results are conditional. Everything is based on assumptions. But so, and it is a detailed rebuttal of the debate. You should also read the opposing side and their views and so on. At the end of the day, that's all I can say. You have to kind of decide for yourself, which is why we're making all the data and code and everything public. And I've told my student also, don't listen to me. I might be crazy. You should decide for yourself. Thank you.
So, hi Rameez, I have one question. Yeah, so DAISY data, for example, that measures the baryon acoustic oscillation, they look into quasars all the way to whatever redshifts up to 2.1, 2.2.
Yes.
So your conclusion holds if you expand your data set for your quasar anisotropy studies?
The AC data is available only over a small region in the sky, right? It's not all sky. Because it's ground based, and they do a targeted spectroscopy of a previously selected photometric catalog, I think. So we cannot currently expand our analysis to include that data, because to measure a dipole you need at least like 50-60% of the sky, otherwise the uncertainty significantly blows up. But for example, people have used catalogs which have only such limited sky coverage, and they do similar analysis, and the error bars are so large that they will keep insisting it is all compatible with the standard model. But it's also compatible with us and everything else. So, for example, it's basically like this green curve. It's compatible with our result. It's compatible with the purely kinematic interpretation of the CMB dipole. So if you don't have a big enough catalog with a large enough sky coverage, this is what you'll get. You can't say anything conclusively. So then, because the null hypothesis is that the CMB dipole is purely kinematic, you can always weigh in on the side of the mainstream opinion.
Okay, nevertheless, even the DAISY data does not support lambda, because if you run back, if you redshift the lambda, you get lambda equation of state something smaller than -1, which is non-unitary clearly.
So yeah, and you get this whatever phantom dark energy or these tasteless things that cosmologists introduce because they don't know what to do. But the DAISY has also been interpreted as what evolving dark energy, and I mean I think this will keep on going for a while until people realize that all of this has nothing to do with interesting physics we do in the laboratory. So it's become a game of just fitting data, I think.
That it has always been one. Anyway, thanks.
One more question.
So I was just going to ask about the dark matter that you commented on. So what do you think is the problem? I mean, we seem to have pretty compelling evidence from CMB and the galaxy cluster surveys and so on. So what do you think is the problem with that? And I think that say that it is a problem.
Well, the CMB evidence for dark matter again is that there is omega m being fitted from the CMB assuming the Friedman equations and small perturbations around it, and that omega m is more than you count from you any estimate for omega baryon, right?
And so matches up well with the galaxy cluster also, I think.
Yeah, so now galaxy cluster is either from lensing, which also again assumes the Friedman-Lemaitre-Robertson-Walker model, looks at the lensing potential in perturbations around it. So there is a nice essay by Jenny Wagner, who won a prize for courageous science in Germany. I can send you this essay if you send me your email, which kind of explains how all lensing inference of for the existence of dark matter is actually circular logic around oversimplification.
No, but also the growth of perturbation from CMB time till fairly late time. All of that seems to form a pretty consistent picture.
So the growth of perturbation is compared, what is measured is compared against expectation from theory. The theory is based on Newtonian linear perturbation theory. Christos Sagas, for example, the same mathematics relativist I'm talking about, he has estimates of this from covariant linear perturbation theory. There is a non-Newtonian linear perturbation theory, which predicts a much faster growth rate, which then suggests that you can do away with dark matter and you don't, as in, basically this entire linear perturbation theory business are assuming a background is not mathematically well defined, in my opinion. It's like saying e raised to x equals 1 plus x. Okay, it's valid in a small regime where the density contrast perturbation is much smaller than 1, but that does not apply to the real universe. So that is my opinion on that matter. And then the main evidence for dark matter, historical evidence, is rotation curves. But rotation curves are also Newtonian, and there is a paper by Maria Teresa Crosta, and more recently David Welshire is about to put one out using the Raychaudhuri equation, which shows that corrections from gravito-electromagnetic effects, which are the vectorial and tensorial effects of gravity, which are there in GR but not there in Newton's gravity. If you just include the corrections from that, you do get faster rotation in the outer parts of any galaxy. So you don't need at least a portion of the dark matter you don't need. You can, of course, never fit.
Sorry to interrupt, but a separate explanation for each one, right? But there's no single explanation for all of them.
No, the single explanation for all of them is that the evidence for dark matter is always within the context of Newtonian theory. If you abandon absolute notions of space and time and embrace, Einstein's basic philosophy, which is also what then I say the rest frame of the universe is not a real thing. It's what I'm saying is something along the lines of what Einstein meant by general covariance, right? I mean, with recent math, we don't think of coordinate systems as a real thing. We think of them as an artifact we are introducing into nature. They don't a priori exist in nature. So if you embrace the idea that the universe evolves according to actual general relativity and not linear perturbation theory or Newton's gravity, then all of this is explained by that notion. Of course, computing it is very difficult because it has deep philosophical implications. It's we can talk at length about this. There are hundreds of papers about the whole issue, and people just ignore it and brush it under the carpet, I think. So it's I'm not introducing any new physics or separate new bits of physics to explain each bits of dark matter. What I'm pointing out is that each evidence for dark matter is Newtonian.
Just a clarification. So you're saying there is room for some dark matter, but not to the extent that is being claimed from the rotation curves. Is that what you're saying?
So until we are able to exactly calculate the actual expansion rate of every point in the real universe, and solve something called the averaging problem and so on, we'll never be able to accurately say so. But directional analysis in that direction of going beyond linear perturbations or abandoning ideas of symmetry strongly suggests that you need less and less dark matter. Now, the idea of dark matter is, of course, something that from a particle physics point of view, if you have any new stable massive particle, it is a candidate for dark matter, right? So the idea of dark matter cannot be killed from cosmology alone. it requires all of us to talk to each other honestly, I think.